Looks like we're just about there, folks. Welcome back, everyone. It looks like we can start. Welcome back, folks, and congratulations on getting through the third exam. I'm not too far along with the grading on those, I have to admit, sorry about that, but I do intend to have them fully graded sometime over this weekend. I'll be able to turn them back in the hard copies in class on next Monday, and for the other copies for the online class, I'll just email them right back to you as soon as I get them graded up. Well, with where we're at so far, we're going through the last section that we're going to cover in section or chapter 11, the Taylor and Maclaurin series finally. Really, we've been dealing with Taylor and Maclaurin series for a little bit now. They came up in section 11.9, 11.8. We just didn't call them that yet. But now we're going to finally develop what we mean by Taylor series. But this is a pretty big section, so it's split into two. Part one and part two down below here, we'll take a look at on Thursday, potentially finishing on Monday's class. We'll see where we'll end up. So this is week 13. That's next week 14, just an ordinary week. Then we take a whole week off. That'll be great. I'll still be available for email, things like that. If you have questions, if you're working on homework, I will still try to be getting caught up on grading and those kinds of things. So don't hesitate to email me, send me graded work if you're working over the break. Then when we come back on this week, we're just about done. December 2nd. On Monday, we'll have a full class day. On Wednesday and Thursday, we're pretty much just going to be reviewing, potentially finalizing the last section on Wednesday. But I think we're in a great space for where our course is right now to have 2 full review days on this week here. Then our final exam is at a really terrible time. It's from 8 to 10 p.m. for the in-person section. That's really awful. If that doesn't work with you, I do also have another final exam from 5:30 to 7:30 p.m. in this classroom as well. So just let me know. I'll probably mention that a couple times before we get there. I'm not opposed to you wanting to take the exam early, since I understand 8 to 10 p.m. is like the worst time to take a final exam, in my opinion. Well, any last questions or comments, folks, with where we're at or where we're going? Or anything at all? Okay, well, let's finally finish off the last section of chapter 11. Just to kind of point where we're going, when we get to this problem right here, I would say that this is a fantastic application of Taylor series, Maclaurin series. It's just an ordinary differential equation, and it's a basic looking one. But a differential equation like that can come up in physics, it could come up in chemistry, biology, engineering, in all sorts of contexts. Solving this one is actually difficult. It requires Taylor series, and we'll see why. But before we get to that, let's start with part one of the notes. We want to formally define what we even mean by Taylor or Maclaurin series. So the first thing we've got to do to get there is take a function f, assume it has a power series representation centered at A, and let's just write it down in sigma form and expanded form. So a power series representation would mean f of x takes a summation as we go from 0 to infinity. The 0 there is curious, but we're almost at a good spot to answer why it starts at 0. Then we take something called Cn. These are the coefficients. We multiply that by x minus the center, A, to the nth power. The power on this group here is why we call it a power series. And this is the format in sigma notation. If we were to put it in expanded form, all we're doing is writing out the series, and it goes like this. We'll go C naught. That's plugging 0 here, and plugging 0 on this group gives us a times 1 plus C1 times x minus A. And then it just keeps on expanding in this way. C2, x minus A squared, C3, x minus A cubed, Let's add a few more since we'll probably need them. C4, x minus a to the fourth power, and C5, x minus a to the fifth power, and so on. It goes off to infinity to mean we have infinitely many terms altogether. And these power series have lots of interesting applications. For example, just in the simple step of taking sine 1.2, plug it into your calculator, you're getting output out. A calculator like, say, the TI-83, TI-84, is using either a Taylor series or a Maclaurin series, depending on your problem, to do that approximation. That's kind of amazing in a certain sense. They're really doing this, a linearization, but they're adding more and more terms to give a high level of accuracy. This is already the first two terms of a Taylor series. That would be the constant term, and that would be the next term right after. That's what we're going to do next. See if that's really true by coming up with the value of all of these coefficients for this power series expansion. But first, any questions, folks, with the format of this power series here? Really just kind of a review problem in a certain sense. Okay, let's get to work on this then. If we're going to come up with a formula for the coefficients, really, that's kind of hard, but you can get your C naught immediately by taking F at one particular value. Anyone see what you can throw in there to determine the value of C naught? In other words, what's a good choice here if we want to calculate f of x? Good call. Could throw in an A. That's the center, and it wipes out everything after C naught. They're all just gone. That's what we were discussing in 11.8. There's always one value where your power series guaranteed will converge. So throw in an A. And we get C naught, just that very first term. So that's one down, infinitely more to go, but it gets us started. To get the next, what we would love to do is repeat this step right here. And to do that, it'd be convenient if C naught was just gone, as well as x minus a. To do that, just take f prime of x. The moment you differentiate this entire expanded form, or if you differentiate this format right here, you can solve for C1 next. C naught is just a constant, so that derivative goes to 0. Derivative right here will give us C1. We have to differentiate all of the terms, so let's write them down. Plus 2C2 x minus a plus 3C3 x minus a squared. Now we're down to this one, same pattern. 4 times the coefficient C4 that we want to solve for, times x minus a cubed, plus 5C5, x minus a to the fourth power. And don't forget there's infinitely many terms, so I'll put the dot, dot, dot there to express it. And it's just a new power series. The one for f prime would have the same radius of convergence. But now we can solve for C1 right away. Take f prime of a, same exact trick. And all that's left is C1. Well, that's two coefficients down. We need infinitely many coefficients. But if we do this enough times, we will see a pattern and we can deduce what the formula should be for all coefficients. Any questions, folks, so far on getting that value? Okay, let's take a few more derivatives until we start to see what the pattern should be. So we're going to f double prime next. So f double prime of x first kills this constant, and we're left with twice C2. Over here, we'll have 6 times C3, but this is a really unusual spot for us as math students. Usually we simplify everything as we go, but we're pattern hunting this time. It's a really, really good idea, even though it goes against our natural instincts, to write the answer like this, 2 by 3, x minus a. If we just multiply these together, we're going to lose the pattern. And this is something we're going to try to do whether we're on this problem here or any problem coming up with the Taylor or Maclaurin series. Continuing on, we have plus 3 times 4, C4, x minus a squared, plus 4 times 5, C5, x minus a cubed, plus, and then so on. Then same standard trick, right down below, we can calculate f double prime at a. That wipes out everything by the red dot to the right, and we're left with just 2c2. That's possibly, well, there's a pattern there. It's just hard to see so far. Anyone happen to guess what it would be? It's a factorial, good call. Let's write this out right here. This now implies if we solve for C2 equals f double prime of a divide by 2 factorial. Since 2 factorial is 2 times 1, we still have a 2 here, really. Let's do the same on this one. This implies C1 is f prime at a divided by, well, you can always divide by 1. And good news, 1 is 1 factorial. Here's where it gets weird, though. Remember way back when factorials first came up? We have a couple conventions. One convention is 0 factorial equals 1 by convention. It's not my favorite expression to say something's true by convention. What we're expressing is mathematics is like a game with a rule book, and we're inventing our own rules here. When 0 factorial comes up, we will write it as a 1. The only reason we do that is if we didn't do that, we would have to break up our power series. We'd have to start with a constant term, then go at 1 to infinity to avoid having to write that down by convention. But if we take that as a convention, and the more math you take, it starts to become a really good convention. There's actually good reasons for that. Then we can come over here and say, this implies C naught equals, we're going to write down the next weird thing by convention, f0 of a divided by 0 factorial. f0 of a, when it comes up, is just a way to say f of a. In other words, no derivative right there. There's the first derivative with C1, second derivative with C2. And if this pattern continues, looks like we have a formula. But any questions, folks, with producing this part of the pattern so far? Okay, let's go through one more differentiation process. See if we really get a 3 factorial. Looks like we will. We have a 3 times 4 right here. And then that's going to be our final step in the derivation. So let's go f triple prime. Instead of putting 3 slashes, which is no harm, occasionally our author likes to go this way. Just like f0 of a is the 0 derivative, just a way to say f of a, f3 is now the third derivative at x. Let's just write it this way, just so it's clear on the notes when we go to use that again. So the third derivative is going to wipe out the constant. Over here, we'll have 2 times 3. Over here, it's now plus 2 times 3 times 4. And at that stage, you could have just written that as, looks like a 4 factorial, times x minus a plus 3 times 4 times 5. Oh, I missed one thing. Let me look again. I had 2 times 3, x minus a. Oh, geez, I missed a couple things. Sorry about that. That should have been 2 times 3. I omitted that C3 on that one, but not the others. That's really weird. So when we went to differentiate, that should have been 2 times 3 C3 plus. Let me highlight that omission right here. Always sucks to make a mistake by just not copying something down, right? So then we differentiate here, 2 came down. Differentiate here, we have 3 times 4 times 5, C5, x minus a squared, and then a bunch of other terms over there. And here's our next step. Take the third derivative at x, or excuse me, take the third derivative and plug in a for x. We do that, this is the only surviving term, 2 times 3, C3, but we can just write that as 3 factorial C3 at this point, which then implies C3 is the third derivative at the center, A, divide by 3 factorial. And notice the pattern. Constant term has the function, no derivative, divide by 0 factorial, first derivative divided by 1 factorial, and that appears to continue. Turns out that's actually true. We have now this formula. The nth coefficient of the power series is going to be equal to the nth derivative, where we understand if we plug n right there, it's not the derivative, just the ordinary function. Evaluate at the center, divide by n factorial. Because factorials come up, that means ratio test is a good way to test our power series or Taylor series or Maclaurin series for its radius of convergence. And now this is the coefficient that goes into this. We wrote up at the top of the notes. F of x equals a summation as we go from 0 to infinity. This is why our power series starts at 0, because we begin at the 0th order derivative, in other words, the original function. It's Cn, let me move that out of the way first, times x minus a to the nth power. But this right here tells us more. We now know all of the coefficients of this power series, which is kind of amazing in a certain sense. It's a summation from 0 to infinity of our original function f is an infinite sum involving all orders of its derivative, so they have to exist, evaluated at a divided by n factorial, and then multiplied by x minus a to the nth power. We'll call this thing a Taylor series centered at a. If a happens to be 0, then it's a Maclaurin series. And our book has a nice little blurb on the side margin of the mathematicians Taylor and Maclaurin who came up with these things. But we've got it, folks. This is what we mean by Taylor series or a Maclaurin series. It's just a specific kind of power series. And our author reminds us we did these in 11.9. We were looking at Taylor series, well, more specifically, Maclaurin series mainly in 11.8, 11.9. Well, what we're going to do now is just figure out how to take a function, come up with this power series right here, whether the function is sine, hyperbolic sine, a natural logarithm, or exponential, and so on. Any questions at the moment with the derivation? Okay. On these notes, because we're really kind of synthesizing a lot of stuff from the last half of chapter 11, that's what this review information is all about. So it's just a review on what a power series is, what the convergence looks like. This is what we were doing in prior sections, 11.8. If we have to differentiate a power series, these are the methods we looked at 11.9. And because as we mentioned, the ratio test is fantastic, it's also posted here. So this page is just a big review document that you might come back to synthesize that information. And this is where the next notes come into play. This is just summarizing what we were doing on our own derivation. If a function f has a power series representation at a center A, the coefficients are automatically given by that formula that we derived. So the total power series is written in this way, and we'll call it the Taylor series if it's centered at A. If the center is 0, it takes on this more simplified format. Instead of having the nth derivative at A, we do the nth derivative at 0, and this is x minus 0, simplifying to just x power n. So now it's called a Maclaurin series in this format. Well, that's a lot of just summary information. This is where the real meat of the notes is. We are going to come up with our own Maclaurin series for that function. Our author actually does this one. So if you've already done the reading, I'm sorry, we're going to do it again, but I feel like that's a good starting one. Just not going too crazy on our first example. So we want to find the Maclaurin series for e to the x. Using the definition of Maclaurin series, that means we're going to derive it from scratch. Then at the end, this is easy to forget. I guess highlighting could help me. We also want to find its radius of convergence. Essentially, the ratio test is going to work on every single one of these situations. So we're coming up with this right here for the Maclaurin series. Here's how it starts. Because we're doing a Maclaurin series, it's not a bad idea to say center is a equals 0, just as a reminder. And now we are coming up with a pattern, just like we did in section 11.1, section 11.2, finding the nth term of a series, for example. We need the nth coefficient of a power series. So in our two-column system, we start off with f of x. Immediately to the right, we calculate f at the center, 0. That's e to the power 0 for a 1. Oh, that's too much yellow highlighting. Let me just convey it this way. If it's a Maclaurin series, then the center is at 0, and our setup starts this way. Now, just like what we did in our derivation for the coefficients of the Taylor series, we need to start taking derivatives. But you can see why this is probably a good starter problem, looking into a pretty abstract concept. Derivative of e to the x is itself. On the right, we need the derivative of f at the center 0. It's still e to the power 0 for a 1. And so this is really something you probably already see the pattern on. Let's do one more just to say we worked hard on it. Here's second derivative at x. Still e to the x. So that means the second derivative is 0. It's still 1. And then we take all this information with this goal in mind. We need a formula for the nth order derivative at the center is 0. Understanding that when we place 0 right there, we're on row 1, where it's not a derivative at all, just the function. But this pattern continues, right? So that means it should just be a 1 right away. I would consider this step 1 in the derivation of a Taylor series or a Maclaurin series. Work out a two-column system with the goal of discovering this formula right here for the nth derivative. Any questions to that step so far? Okay, so it's a great starter example because that pattern is easy to detect. We'll do some more challenging ones on these notes to mimic the homework and typical exam problems. Here's what I would consider a great immediate step 2. You want a formula for Cn. Cn goes Fn, the nth order derivative at 0, divide by n factorial. So all we're doing in this step is taking that, plugging it in right here. So the coefficients are all 1 over n factorial. So not a major step. Whatever you get here in step 1, you just divide it by n factorial, in other words, and you're off to the right start. Factorial comes up only because in our derivation, when we took all those derivatives, factorial just came up naturally. Beyond here, here's step 4. We're putting all of the, excuse me, I must have skipped a step. Counting is hard, I think. Step 3, we're putting everything together into the power series. And I think it's a good idea to emphasize the function you're specifically working with, e to the x. E to the x is a wonderful exponential function that we all know and love. We've used it for years, right? But here's another take on it. E to the x can also be rewritten as a summation from 0 to infinity of Cn times x minus 0 to the nth power. Again, this is the center. It's kind of silly to write that for the Maclaurin series. That's just tying up the original formula. This will always just be x to the power of n when it is a Maclaurin series. So altogether, it's a summation from 0 to infinity of this whole thing, 1 over n factorial, multiplied by x to the power of n. And all we need to do to finalize this is come up with the associated radius of convergence. So my claim is that base C exponential is really just that. We want to find out what is the domain of this thing as a power series. So that's the purpose over here, coming up with its radius of convergence. But any questions so far, folks, to this step? Rather, that step? Okay, and I think I've done this once before in class. Someone had a comment about this earlier, but it's a great idea once you do this kind of thing to just check it out on Desmos, your favorite graphing calculator, Mathematica, or something like that. Plug in your original function. There it is, the exponential we expect. And, well, this is the power series for it. Let's expand it out. It's not required, but if you like, you can take e to the x and write your answer this way. Plugging 0 inside this is going to give us x to the power 0 divided by 0 factorial, which is a 1. Plugging in a 1 inside is going to give us just x divided by 1 factorial, so just x. Plugging in a 2 now, it's x squared over 2 factorial, which is 2, and so on. X cubed, 3 factorial, x power 4, 4 factorial, and on it goes down in the line. When you're in Calculus 1 and dealing with the linear approximations, this part right here is the f of a for the linearization, and this part right here, x, is the f prime of a times x minus a part of the linearization. But what we have now is way more terms, meaning we can get massively more accuracy here if we needed it. And now, back in Desmos, here's how the approximation starts if we're only using finitely many terms. That's what your TI-84 calculator would do if you calculate, say, e to the power of 0.3 or something random like that. Plug in 1 to start. Horrible approximation of the function, right? But that's just a constant function. Add x. And you know what it looks about, right? That's the linearization of the exponential function at 0. And if all of your approximations are very close to 0, the linearization, the blue curve, is not too different than the red curve, the exponential. You get some big problems when you're at, say, 1 or beyond, or -1 and beyond, unless you put in the next term, plus x squared over 2. It bends our linearization and starts to actually map it a little bit better to the red curve. Now we have a bigger range around 0. So your calculator, again, if you're going to calculate, say, e to the power of 0.3, this does just as good of a job. Your calculator probably uses a few more terms to give all those decimal places you typically see. But if you're doing e to the power of maybe 2, that's going to be less of a good job. We see already around here at about 0.5 and greater, the Taylor polynomial, or excuse me, the Maclaurin series and the curve start to differ a lot. So there's 2 approaches. Add more terms, or if you're really curious about e squared, maybe our power series should be centered around e power 2. That would allow us to calculate, for example, e to the 2.1 or 2.3 a little bit better. But just to see how this goes, let's add a couple more terms. It's our first Maclaurin series, so why not? X cubed over 3 factorial.
So you're sorry. So you're just saying by changing the center, you kind of change how accurate it is at that point. Like it's more accurate at the center, or it's modeling the center of the function better.
Exactly. So
Okay.
if our center is at 0, exactly, then it's going to model the function exceedingly well around 0. Absolutely. But as we wanted to calculate around e power -4, our center should be around -4 as well, like you said. Then our approximation is better out here, worse out here. But in either case, the more terms you add, the better the approximation gets regardless. The wider the domain gets for higher accuracy. So here's x power 4. We'll make this our last one. 4 factorial. Notice it's now going close to -2. On the right, I don't have any problems so much anymore, unless I'm more, again, closer to +2. And this is just 5 terms. That's not too much to worry about. It's not too hard to calculate a for loop in a computer with 50 terms, no problems. If you did that, then this is a astoundingly great approximation. Again, unless you're somewhere away from the center, farther away. But in either case, we've got our power series representation here. This is just the expanded form. And our answer is complete. Let me just box it out to emphasize our answers here. Once we come up with radius of convergence. But that's not so bad. That's just going to be ratio test. Any questions first, folks, before we launch into that test? Okay, so if we test this power series here using the ratio test, it will be limit n to infinity, the n+1th term divided by the prior term an. It's the limit as n goes to infinity of x power n+1, n+1 factorial times n factorial divided by x power n. So that's our standard steps with the ratio test down here. Finally answers why we did so much ratio tests with factorials everywhere and weird kinds of factorials. They just come up in this context. So now the limit as n goes to infinity of, when we go to cancel, this is just going to be absolute value of x in this location. This n factorial cancels with n+1 factorial, leaving just an n+1. That's kind of tricky. Does that make sense to folks on how we got n+1 here? Okay, then take the limit as n goes to infinity, automatically 0. We have something finite and constant up in the numerator, divided by something that grows without bound. So the limit is 0 for all x not equal to 0. I mean, if x was 0, the limit would have, come out as 0 as well. No, that's a limit of 0 for all x, rather. Sorry, I'm not too sure what my brain did there. That is a limit that equals 0 no matter what x is, even if x is 0 as well. But that's less than 1. Less than 1 in the ratio test implies convergence. And this works for all x. That means the radius is infinity. I usually write it up here next to the power series. You don't have to do that, but it's good to place them together just to emphasize that's the result there. So we now have a new way to write e to the x. It's an infinite sum, x power of n divided by n factorial, and the domain of that is all real numbers. So that means I only put down finitely many terms here, but if you really go to infinity, blue curve and the red curve do match exactly. It's a type of limit since we're going to infinity, but that's kind of nice to know that e to the x converges to this, its power series. Well, that's one down. Usually the hard step is right here coming up with a pattern. So that's what we're going to be focusing on a lot on our next problems. And it looks like our next one is hyperbolic sine. Well, if it's hyperbolic sine, we should write some stuff out. Sinh or hyperbolic sine, or sine h of x, however you like to say it, goes e to the x minus e to the power negative x divided by 2, and cosh, hyperbolic sine, or hyperbolic cosine, just about the same, except you have a plus in the middle in the numerator. E to the x plus e power negative x divided by 2. And although this is a side comment, notice the exponentials come up. And we have a formula for an exponential. That means you could take this formula right here and derive your hyperbolics through e to the x if you really wanted to. It turns out e to the x, if you use complex numbers, also encodes sine and cosine functions. That's really pretty bizarre as well. Those are other interesting side topics we'll try to get into at the end of these notes, in part 2 rather. But for the moment, all we're trying to go for is the Maclaurin series for hyperbolic sine h. So since it's a Maclaurin series, we have a center, a set to 0, and this is how the work starts. Begin with f of x, sine hx. On the right column, go f at the center. Hyperbolic sine at 0 places a 0 here. That becomes a 1 minus 1, giving us a result of 0 on that first computation. Oh, geez, I'm not sure what I clicked on. And on the next line, we just go to the derivative. So here's f prime of x next. Derivative of hyperbolic sine becomes hyperbolic cosine, so cosh x. This is a derivative, so we go f prime at 0 next. And for plugging 0 here, it becomes 1 plus 1 divided by 2, so we get a value of 1 out next. So we go 0, 1. We want a pattern, and it looks like it's possibly going to alternate in this kind of way between zeros and ones. But we should calculate a bunch more just to be sure. So f double prime of x, any volunteers for this one? Is it positive or negative hyperbolic sine? Good call. This is the one. Sorry, say again?
Oh, go ahead. Go ahead. Yeah.
Yeah, this one comes out as a positive hyperbolic sine, breaking what we would expect if it was just an ordinary trig function. So it's back to sine hx. And that means f double prime at 0, back to 0 on this one. If we take the third order derivative, it'd be, I'll go this way, the 3 instead of the triple prime. Up to you how you like to convey it. Derivative of hyperbolic sine is back to hyperbolic cosine of x. So third order derivative here at 0, back to a 1 again. And it looks like these things are just going to alternate in that pattern forever. But this is tricky because half of the terms in our Maclaurin series are now 0. The other half of the terms are 1. And we don't want to write down a power series where half the terms are 0. This is a situation where we need to re-index our power series, which is a little bit tricky. Here's the way I try to organize whenever this comes up. We re-index whenever there's an alternation between something 0 and non-zero. Alternates between 0 and non-zero. So we will re-index the sum. First, we look at how the index starts. Here, it's at n equals 0, n equals 1, n equals 2, n equals 3. And now we can make an important observation. At the even indexes, it's always 0. At the odd indexes, it's always 1. So we need a good formula for even and odd out of nowhere. Here's the formula that we can use. 2n is even. That was a weird thing to say. 2 times n is even for all integers n. And likewise, if 2n is even, increment it by 1, you are automatically to an odd integer. So 2n plus 1 is odd for all integers n. So we need that little extra description to describe all orders of our derivative. So let's break this up into evens versus odds. So on our next step, we'll say f at an even order derivative, I got to get those right, are always 0, with the understanding that at 0 itself, we're just talking about the function. So f at 2n is always 0. However, we have f at an odd order derivative, 2n plus 1, evaluated at the center 0, for example, on this one, always produces a 1 instead. So this gets us started. Any questions so far, folks, about the evens and odds? Okay, so after we have the formula for our derivatives of all orders, evens versus odds, 0 and 1, we can now say, here are the coefficients. This is the coefficient at every even index. It involves the derivative divided by a factorial, but the derivative is 0, so it's also 0 here. It's kind of nice. That means we're throwing away half the terms. They're just 0. But over here, we write down C, 2n plus 1. So this is going to be the coefficient whenever the index is odd. That means automatically the denominator is an odd number factorial, the same value of the index, 2n plus 1 factorial, coming from right here. The numerator comes from this, and it's just a 1 altogether. So we're just about there. Reindexing means we're doing this on the next step. We go sine hx, that's the original function we want a Maclaurin series for, is now a summation as n goes from 0 to infinity of, we take this thing right here and we multiply it by x to the power of n. So it's going to be x power of n. It's really x minus 0 to the power of n, but whenever your center is 0, it's more natural to just write this out. Divide by 2n plus 1 factorial. Actually, let me take one additional step just to connect the dots. C 2n plus 1 times x to the power of n. Well, we came up with the formula C2n plus 1. We just kind of highlight it that way to convey. So now it's a summation from 0 to infinity of 1 divided by 2n plus 1 factorial. So that's our power series. We'll really call it officially a Maclaurin series once I remember to put in this, sorry for that omission, x power of n for hyperbolic sine. Let me just throw it into the numerator. I think that's a good spot for it. All we need now is the radius of convergence, and we'll be on our way with this one. So hyperbolic sine comes up into this format. We mentioned that we are re-indexing all of these indexes. It's kind of hard to see how we re-indexed it, unless we expand this a little bit further. So let's do just that. So we have hyperbolic sine is written most compactly like this. This is how the back of the book answers are usually formatted. But we can also say hyperbolic sine of x is also plug a 0 inside here, and we will get x to the power of 0 is 1, divide by 1 factorial, just giving us a 1 altogether. Then go plus. We're plugging 1 inside here, so that means we'll get x divided by 3 factorial. Plug a 2 inside there, and we'll get x squared divided by 5 factorial altogether. Oh, and I think I did make one additional mistake on this one. Sorry for the errors on this. If it's 2n plus 1 down below right here, it's also 2n plus 1 right here on the exponent position. So when we plugged in 1 right here, we were getting x cubed. I'm kind of glad we expanded this out. When we plugged in 2, we were getting x power 5 divided by 5 factorial. That just seems a little bit more accurate. That seems like the real pattern we should be taking. But this index is not the same as this one right here. It's grabbing all the terms that happen to be odd, giving us these values. So that's why we see x cubed, x power 5. We don't see 0 times x squared any longer. So let's write out one more. X power 7 divided by 7 factorial. And so on. So 2 ways of expressing it. This is the compact form with the summation symbol. And this is just another way to convey. I think I sometimes like that value a little bit better because it's a lot less abstract. We're looking at something more concrete. But the more and more you deal with power series, the more often it's just written this way. It's up to us to expand it if we want to visualize it a little bit better. So last steps on this one is just finding the radius of convergence. But again, I think this is a pretty tricky problem. This happens whenever it's a hyperbolic function or a trig function. We have another trig function we'll deal with. Any questions at all, folks, on this whole reindexing even odd business?
The even odd thing, kind of the 2n plus 1, kind of, it's not clicking for me, but I guess.
Well, one way to think about it is if you grab any even integer whatsoever, let's say 14. My claim is you could write it as 2 by n for the right value of n, and it would be like this, 2 by 7, and that's the n value in that formula. If you grab something random, like say 31, then this could be rewritten as 2 by 15 plus 1, and that's the 2n in this problem, so the n would have to be a 15.
The stage, whatever, shouldn't that use C of 2n, not 2n plus 1?
So
Since f of 0 at when f of x is hinge, it's equal to 0.
let me see. Where are we looking at? Sorry.
Yeah, like right there.
So since at 0 is 0 for 0, and 0 again for 2.
But when 2n is it when 2n? Yeah.
So at 2n, that would be for this one right here, the n would be a 0 value,
Yeah.
giving that line. And then for this one right here, the 2n would update, well, the n itself would update to a 1 right there to give that 0 value again.
Yeah, do we just not all the zeros?
Yeah, that's the idea. We're trying to eliminate all of the zeros altogether when we go to write out this format. So reindexing is a way to say, we're trying to just delete these rows outright and focus on just the non-zero stuff.
Yeah.
I'm
Other questions
comparing
about that?
yeah, sorry. I'm comparing the two problems. Can you explain on the first problem that we did why Cn is equal to 1n factorial? Sorry to go back. I was just comparing them.
Yeah, so the Cn itself by formula is this right here. So when we go to derive Cn, we're always dividing by a factorial. I'm just peeking at my color coding. Let me maintain it up here. We take the result of whatever we derived for the nth order derivative and just divide it by a factorial. But this one was n itself. So the index n matches down right here. We found that the derivative is always 1. So when we went to write Cn, we just divide by that n factorial. But here's where it gets a little bit weird. When we re-indexed, the 2n plus 1 right here is also the 2n plus 1 factorial in that location, and the 1 goes down to a 1. So in other words, Cn itself is always nth order derivative at a, Ra is a 0, divide by n factorial. But if you change this, then whatever you put here also goes here, and it also goes here. I made that mistake legitimately, forgetting that part. Does that help out with that question about the Cn part?
Yeah, thank you.
Yeah, absolutely. Other questions so far? These are all excellent questions, by the way. These are the right questions that learning this or seeing it for the first time, you would definitely want to ask. But sometimes it's hard to know what the questions are even are when you're looking at this kind of material. Well, so far to reconvene, we derived hyperbolic sine. It's that as a Maclaurin series, or that is in its expanded form. Annoyingly, we're not done with it. We want to find its radius of convergence. But you know what? You can sometimes make pretty good guesses here. If there is just x to a power in the numerator and a big old factorial function in the denominator, it is probably true that the radius is infinity. So let's call our shot and just write it in right here. I'm going to box this out just to express That's our answer on this problem. I don't like boxing out our answers, but this is one of those problems where you get your result in the middle, and then you have to do a little bit more. So this is us justifying the radius of convergence really is infinity. We hit it with the ratio test again. As n goes to infinity of an plus 1 over an, let's write this out carefully. The limit as n goes to infinity of this part first, an plus 1, it's going to put an n plus 1 right there by the red dot. But when you put n plus 1 there, 2 distributes, and you get x to the power of 2n plus 3 altogether. I think it's really kind of easy to miss with this kind of thing. Likewise, n plus 1 right there, distribute the 2 through, you get 2n plus 2 plus 1. So it's a 2n plus 3 factorial down below. So that takes care of the successor term in the numerator. Now we work with an. That's not so bad. We flip this around. It's going to be 2n plus 1 factorial divided by x to the power 2n plus 1, and we close the absolute values. So if we can maneuver through this limit and show that this limit is 0 irregardless of the value x, radius being infinity would be true. And by the way, these are what we really always want to say, because it means we have found a Maclaurin series that represents our function on the entire real number line. There is not a place where this is going to fail to converge. But sadly, we really have to show it. So let's get through the nitty-gritty details. We're taking the limit as n goes off to infinity. Let's be careful with this one because this is kind of a wonky factorial function. In the numerator, we could rewrite this as, let's see, let's factor out x squared, leave behind x to the power 2n plus 3. Or excuse me, 2n plus 1 rather. That's no factoring of the plus 3 there. We have a 2n plus 1 factorial. That means we want to expand this one in this way. A 2n plus 3 factorial is a 2n plus 3 multiplied by the next factor, 2n plus 2, multiplied by all the prior ones, which will be 2n plus 1 factorial. We're stopping there because on the next fraction, we have 2n plus 1 factorial. Divide by x power 2n plus 1. And here's the fun step. We have a cancellation going this way and this way. And now everything left over here is positive by default. The absolute value just totally vanishes. And we get, if you prefer, you could take x squared and leave it outside the limit. The limit is as n goes off to infinity, so x is regarded as a constant. All we have is 1 over 2n plus 3, 2n plus 2. That's a rational function in the variable n, and so its horizontal asymptote as we go up to infinity is 0. We've got an x squared times 0. No matter what x is, that's still a 0, which is less than 1. And that statement right here does imply radius is infinity, because that inequality holds for all values of x. But we established the last bit. It's kind of annoying to do the ratio test out of nowhere, but not all of them have radius infinity, so we have to be sure what the radius really is when we go to calculate these things. Well, that's 2 down. Any questions at all, folks, with these so far? Okay, let's see how we're doing on time. We've got about 16 minutes. I think we might be able to do one more. Let's give it a try. This time we're dealing with an exponential function. It's still a Maclaurin series, so we're still centering this thing at 0. But just as a reminder, we take the derivative with respect to x of a base b exponential to the x power. Our hope is that b is at e, so it's just derivative of e to the x. But this formula is b to the x times natural log b. I think that's an easy formula to forget from Calculus 1, since we don't differentiate those kinds of functions as often as you would have in Calculus 1. So now when we launch into this process, let's say here, center is a equals 0, only because it said Maclaurin series. Good to just reiterate that, I'd say. Start off with our two columns. We have f of x equals 5 power x. And then we calculate f at 0. That's 5 to the power of 0, giving us just a 1. So nothing super exciting so far. And then we start calculating higher order derivatives. The derivative of 5 power of x is 5 to the power of x times the natural logarithm of 5. That means the derivative of f at 0 is just natural log of 5. We only go as far as we need to in order to establish a pattern. So I think for most people, you'll have 3 rows, this being row 1, row 2, row 3, f triple prime of x. Let me say that in a better way. I would say for most people, you would have at least 3 rows. Let's say that here. At least 3 rows is, let's go with needed. If you discover the pattern in 2 rows, that's okay, but it's more typical to do 3 or potentially even more. But the derivative is not too bad. Or if we're differentiating this, you still get 5 to the power of x times the natural log 5 times the natural log 5 again. So we have natural log 5 squared. And so that means the second derivative at 0 is natural log 5 squared. But that already is starting to establish a pattern. We have the second order derivative, natural log 5 squared. We have the first order derivative, and that's natural log 5 to the power 1. Let me try to write that so it doesn't look like a prime symbol. Sorry, go ahead.
On the double prime, should there be a divided by 5?
Let me see. When we're differentiating this right here, it's regarded as a constant. So we're really using the constant multiple rule on that one. Does that make sense there? Gotcha. It definitely looks kind of funny in the format. That's a pretty abstract constant. So we have second order derivative is natural log 5 squared, natural log 5 to the power of 1. And f of 0 being 1, that's just natural log 5 to the power of 0. So if we can match this up, we definitely have a good pattern going on this. We can now say that all of this work is to come up with this formula. The nth order derivative of our function at the center, which is 0, is nothing but natural log 5 to the power n. So we're on our way. If we can get that, we just go through the next methodical steps of come up with Cn and then come up with the whole Maclaurin series. Any questions at all, folks, getting to this line? Okay, it's not too bad once we see what the steps should look like. The weird ones are, again, trig functions or hyperbolic functions. We'll practice more of those as well. But now we could say Cn, just to write down the formula for the sake of memorizing it, is the nth order derivative at 0 divided by n factorial. So that means it comes out as natural log 5 to the nth power divided by n factorial altogether. Once we get here, next step is to write out our function 5 to the power of x as a Maclaurin series representation that goes from summation 0 to infinity, take coefficients Cn, because it's a power series centered at 0, we multiply it by x power n. So here's our finalizing step. Summation from 0 to infinity of, for Cn, we're throwing in all of this stuff right here, so natural log 5 to the nth power, divided by n factorial, multiplied by x power n. My claim is, once again, analyzing this, well, we have a coefficient natural log 5 to the power of n divided by n factorial, so now it's up to whatever wins, this function to a higher power or a factorial function. My guess is still a radius of infinity because of the factorial, But like all the others, we still have to show it. So one more ratio test. Any questions first, folks, with getting to here? Okay, in this part of the notes, once we're all the way to section 11.10, if you don't say ratio test, that's totally fine because it's an understanding that you're pretty much using it just by default and as a guarantee. So in the ratio test, take limit as n goes off to infinity. It's going to be natural log 5 power n plus 1 divide by n plus 1 factorial to start. Then we take n factorial, divide by natural log 5 to the nth power. Next is our standard kind of cancellations. Let me hide that first. We're going to get, oh, hang on, sorry. Looks like I forgot something inside there. We have natural log 5 to the power of n plus 1. That color coding is what's kind of leading me astray. Times x to the power of n plus 1. You definitely don't want to forget that. That's the major reason we are using the ratio test. Multiply by the new fraction that goes n factorial, natural log 5 power of n times x power n. Okay, sorry for that omission of the variable x. Then next we do our typical cancellations. N factorial cancels here, just leaving n plus 1. I think that's kind of a funky way to cancel. Let me maybe do it on the next step. Just so the notes are a little bit more readable. We have limit as n goes to infinity. Natural log of 5 times natural log 5 to the nth power, x times x power of n. And the n plus 1 factorial, a standard simplification is take n plus 1 times n factorial. Then next factor, n factorial, natural log 5 to the nth power, x power of n. My hand is actually getting tired at that point, but I think we've got it. So this will be a little bit easier to track in the notes if we come back to this page. So the factorials cancel, x power n's cancel, natural log 5 to the nth power cancels. And all we're left with is natural log 5, absolute values centered just on that x. So natural log 5, absolute value of x, they're all constants, so they can come out of the limit. So limit as n goes to infinity of 1 over n plus 1. These values of n in the denominator surviving are just kind of a side effect of the fact that there's a factorial in these problems. But you know, sometimes the factorial does go away. We're going to see some other odd problems where the radius is not infinity. But in this problem, finishing it off, we get natural log 5 absolute value of x times 0, which is 0, which is less than 1 for all x, which does imply the radius was infinity as we called it out. But our total answer is right here in the middle. Oh, dang, I missed. I don't know why people go for boxes. I think it's easier to just circle them, but there's the answer right here. Well, we still have more that we're going to try to get to in these notes. We're going to go for Taylor series next of a trig function when we come back on Thursday. And if we have time, we'll move over to the second part of Taylor series, looking at some applications of what we can do with them. I have an application dealing with some differential equation, and we can look into something with a complex number to see how e to the x is actually tied into a formula with sine and cosine, as strange as it sounds. But any last questions, folks, on dealing with these Maclaurin series so far? Okay, well, this is a good stopping point for us then. Have a great evening, folks, and we'll come back to it on Thursday's class. Then it's just one more week and we'll take a well-deserved break. So we're getting there. Have a great one, folks.